Hi, this is Dr. Vev, and I'll be teaching you how to solve a second-order linear ordinary differential equation, or LODE, using Euler's formula. So the differential equation in question can be written either in Leibniz's notation, which would be the left-hand side. The second derivative is indicated explicitly in the Leibniz notation. In the Newtonian notation, I guess Newton did not like to waste paper. The second derivative is just denoted by x double dot, that first derivative by x dot, and so on. Omega here is a constant, and by examining the dimensions of the equation, you can see that the omega must be some sort of frequency, because that's 1 over time squared, and omega must be 1 over time in that case. So how do we solve this? Because we're going to use Euler's formula, the appropriate thing to use is what's called an Euler's ansatz. The word ansatz in German means try something. So we're going to use the ansatz, x as a function of time equals e to the lambda t, where lambda is to be determined. So let's take the first derivative. X dot would just be lambda e to the lambda t. And x double dot, the second derivative, would be another factor of lambda multiplying the lambda here. So I get lambda squared e to the lambda t. Now I substitute this into Newton's form of that equation, and I end up with the following algebraic equation. Lambda squared e to the lambda t plus omega squared e to the lambda t is equal to 0. Now this can be written as lambda squared plus omega squared times e to the lambda t equal to 0. Now when you have a product of two quantities equal to 0, you may have studied in middle school, it means that either one is 0 or the other is 0. So two possibilities we have are that lambda squared plus omega squared equal to 0, or that e to the lambda t equal to 0. If e to the lambda t equal to 0, that would mean that x is 0. Now, does x equal to 0 satisfy Newton's equation? It does. Because if x is 0, x double dot is also 0. So 0 plus omega squared times 0 equals 0. Yes, it is a solution. But it's a very silly solution. It's sometimes called the trivial solution because of its silliness, and the trivial solution is always ruled out in this problem. If you were thinking of a physics example of what this system actually represents, it would represent something like a block spring oscillator. So I have here a wall and a floor, and attached to this wall would be a spring of spring constant K and a mass M, and the floor is supposed to be frictionless, and it oscillates back and forth. X then represents the displacement from the equilibrium position 0, and this equation is actually pretty easy to derive using physical considerations, because by Newton's laws, F equals ma, but F is also equal to the spring force, and the spring force by Hooke's law is negative kx. So if you write down what acceleration is the second derivative of position. I'll transfer the m over to the other side, so I get x double dot equals minus k over m x, and then if I bring everything to one side, I get x double dot plus omega squared x equal to 0. So that omega is actually something like the square root of the spring constant divided by the mass of the object in this example. So this sort of system arises pretty naturally, and you can expect the solution to be of an oscillatory kind. X, when the dust settles down and we solve for x, it has to have sine or cosine components to it, and we will see that it does. And you can also see that's where the Euler formula ties into the whole picture, because Euler's formula is e to the I theta equals cosine theta plus I sine theta, and so the sine and cosine components end up showing up. So let's go with a non-trivial solution, which is the other case, lambda squared plus omega squared equal to 0. Now that has got two solutions. So let's focus on that. Lambda squared plus omega squared equal to 0 means that, but incidentally, for those who are fond of terminology, this is called the characteristic equation in differential equation theory. When you use Euler ansatz, you'll always get an algebraic characteristic equation that is an algebraic polynomial, and it has to be solved. So this gives me lambda equals plus or minus the square root of minus 1 times omega squared, which is plus or minus I omega, because I is the square root of minus 1, as we studied in the complex number video. So the solutions are going to be a linear combination of the lambda with a plus sign and the lambda with a minus sign. So I can write the full solution of this oscillation as A times e to the I omega t plus B times e to the minus I omega t, where A and B currently are complex numbers. Now the reason I chose A and B to be complex numbers is because I know this oscillation does happen in real life. If I take a block and attach it to a spring and set it oscillating, it's going to happen in front of my very eyes. There's nothing imaginary about it. But e to the I omega t and e to the minus I omega t are in general complex numbers for non-zero omega. So if I want the complex numbers to interact with B and produce a real number, I have to have B also to be complex, and that's why I chose A and B to be complex. So the condition that we have to impose is known as the reality condition. The reality condition is that x be real. Now, how do you impose that in the world of complex numbers? Let's go back to our complex plane diagram known as a Gauss-Argand diagram with the imaginary part and the real part here. And let's try to find a way to signal that a complex number is in fact a real number. How would you do that? If I have a complex number z, let's look at its complex conjugate, which is a reflection. So think of the real axis as a lake. The complex conjugate is just a reflection of the mountain in the lake. Okay, so that's z bar. A complex number is said to be real if z and z bar coincide. That's a pretty good criterion. So if you find that there's no difference between z and z bar, it must mean that the complex number was never off the real axis to begin with. So that can be taken as our condition for reality. Z equals z bar implies that z must be real. Let's use that reality condition here. In this case, it takes the form of saying x of t must be equal to x bar of t. So I'm going to do that here. Now also let's, off to the side, let's try to understand what this reality constraint means for Euler's form. E to the I theta is cosine theta plus I sine theta. The complex conjugate of e to the I theta is going to be e to the minus I theta, because if e to the I theta is some complex number in this along this direction with a magnitude 1, e to the minus I theta would be the reflection of that same thing in the fourth quadrant. So that would be cosine theta. As you can see, the real parts are the same, but the imaginary part is going to have a negative sign, minus I sine theta. That shows you that e to the minus I theta is in the fourth quadrant, and it's correctly the complex conjugate of e to the I theta. So armed with all this knowledge, we can go back to our imposition of the reality condition. I'm going to get x of t, which is all this. So I get a e to the I omega t plus b e to the minus I omega t equals x bar. I have to take the bar of everything, a bar, and the complex conjugate of e to the I omega t by this is just equal to e to the minus I omega t, plus the complex conjugate of b is b bar, and the complex conjugate of e to the minus I omega t would be the reflection of that, which is this. So that's e to the I omega t. So we have to solve this equation. That's pretty easy to see. If I compare the like terms meaning the coefficients of e to the I omega t and e to the minus I omega t, I'll get the following system of equations. I'll get that a equals b bar, and B equals A bar. In other words, A and B are complex conjugates of each other. So I don't even have to worry about distinguishing between A and B. So the full solution is x of t is equal to A e to the I omega t plus A bar e to the minus I omega t, with A still being complex. Unfortunately, this is not quite the way that people think about a simple harmonic oscillator, although it's the right way to do it. For example, if you were doing quantum mechanics, this would be the correct way to write the simple harmonic oscillator amplitude in terms of the creation and annihilation operators. But if you are not doing quantum mechanics and you want to be in the classical world and write everything in terms of sines and cosines, you have to do one further step. So let me do that step now. Let me write A equals little a plus IB. That's just a complex number. And A bar then would be A bar minus IB. There's no bar there. It's just A minus IB. E to the I omega t is cosine omega t plus I sine omega t. And e to the minus I omega t would be cosine omega t minus I sine omega t. And let's just stuff everything into there. So I get x of t is A plus IB times cosine omega t plus I sine omega t plus A minus IB times cosine omega t minus I sine omega t. And now I'll assemble the terms together. So I'm going to get A cosine omega t. Now there better be no imaginary terms, because I have arranged this thing to satisfy the condition of reality. So this is the moment of truth when we'll find out if the imaginary terms cancel or not. A cosine omega t, and then I get plus IB cosine omega t, and then I have to do this and this. So I get plus IA sine omega t, and the two i's combine to get minus 1. So I get minus B sine omega t. And now I have terms from this expression. So I get A cosine omega t minus B I times B cosine omega t. Then I have this and this, which is minus IA sine omega t. And lastly, I have minus I and minus I. Well, minus and minus become plus. And again, I squared is minus 1. So that's minus B sine omega t. So correct, we see that, sure enough, we lose all the imaginary things and we just have real objects. So I have A cosine omega t, A cosine omega t. So that's 2A cosine omega t. And then I have B and B. So that's minus 2B sine omega t. So that gives you everything in terms of cosine and sine. Now just FYI, this can also be written as some quantity which I'll call C times cosine omega t plus a phase factor known as phi. That phase factor will fix any initial conditions. And you can see what C and phi are by expanding this out. So ideally, I would like to leave this as an exercise, but let me just quickly expand it out. This is C. Cosine A plus B is cosine A cosine B minus sine A sine B. So all we have to do is compare. Comparing the coefficient of cosine omega t, that is 2A here, and that is C cosine phi here. So we have from this that 2A must be the same as C cosine phi, and that negative 2B must be the same as negative C sine phi, or 2B must be equal to C sine phi. How do we solve this equation for C and for phi? Well, one option is to square and add. If you square and add them, I'm going to get 2a squared plus 2b squared, which is 4 times a squared plus b squared, is equal to c squared cosine squared plus c squared sine squared, which is just c squared because cosine squared plus sine squared is equal to 1. So I'll get the value of c is just 2 times the square root of a squared plus b squared. And then the value of phi can be got by just dividing the two. I'll divide the second equation by the first equation, so I'll get tan phi equals b over a. So I can also write this equation as x of t equal to the square root is 2 root a squared plus b squared times cosine of omega t plus tan inverse b by a. So that completely solves this equation. You don't have to really worry about writing it like this. I can also write it like as something else. I can write it as d cosine omega t plus phi, where d is equal to that and phi is equal to that, and I don't have to worry about calling d anything. But generally speaking, you see how these solutions are related through mere algebra.